Our next presenter is Jeffrey Herrmann. He has appointments in mechanical engineering and the Institute for Systems Research. Jeffrey.
Okay, thanks, Jansen. Okay. Good afternoon, everyone. Hi, I'm Jeffrey Herrmann. I'm a faculty member here at the University of Maryland. I have a joint appointment in the Department of Mechanical Engineering and the Institute for Systems Research. And today I'll be talking about our research on meta-reasoning for robots. I'll go over two projects that we're doing in the area of meta-reasoning, and then I'll finish up with a few ideas of where we're headed. Okay, so the basic idea here in this little cartoon is that we have a robot in an environment, and it has a destination that it's trying to get to, and it needs to plan its path in order to get to its destination. Now, normally, if I'm the designer of this robot, I'm going to decide which path planning algorithm I want this robot to use, and I'm going to program the robot to use a certain algorithm, and it's going to use that algorithm to plan its path. The problem is that although there are many different path planning algorithms, there's no single algorithm that's best for all situations. If I as the designer choose an algorithm that's guaranteed to find the optimal solution, then there might be cases where it takes too long or it takes a very long time to find a solution. If, on the other hand, I choose an algorithm that always runs very quickly, then there might be situations where that algorithm comes up with poor solutions, and it takes a long time for the robot to get to its destination. So the idea of meta-reasoning is to let the robot decide in real time which algorithm it wants to use. Telling the robot to always use algorithm A, I'm going to let the robot decide, sometimes use A, sometimes use B, sometimes use C, based on some type of meta-reasoning policy. So this is the idea of meta-reasoning. So the robot can choose based on the current environment, based on its computational resources, based on how long it has available for planning or whatever. Now this figure includes the kind of canonical three-level figure for meta-reasoning. So here we have the ground level, the object level, and the meta level. The ground level is where the robot is doing something, right? It's moving around the environment, it's sensing the environment, et cetera. And then it's passing its perception, its images or other signals up to the object level, which is reasoning. And here I've included, I know you can't see it, but I've included a schematic of the ARL ground autonomy stack, which is a typical type of object level thing that will do image processing, mapping, planning, all the other things that have to be done in order to tell the robot which action to take. So the object level is controlling the robot. Okay, then we add a meta level, and the meta level monitors and controls the object level. So the meta level, through some kind of meta reasoning policy, determines how the robot should reason. Now, there are many different types of meta reasoning problems and meta reasoning approaches. They might include telling the robot which path planning algorithm to use, or it might be telling the robot how long to run an anytime algorithm, or which image processing object detector to use. There's many different types of meta reasoning approaches. So here today, I'm just going to talk about two projects where we've looked at meta reasoning. Okay, the first one was a project that I and some of my colleagues and many of our students worked on. This includes folks from mechanical engineering and aerospace engineering and systems engineering. And this project was funded by the Air Force Research Laboratory and ended a couple of years ago. And in this project, we were looking at planning and meta reasoning for multi-agent systems with variable communication availability. So we were looking at situations like this, where we've got a small team of UAVs moving around, searching for and intercepting moving targets in a maritime environment. As a ship moves through that environment, they're supposed to be protecting the ship. So this is an interesting problem by itself, of course, but it's even more difficult when communication availability is not guaranteed. And communication availability might be changing over time due to different reasons. Okay. So we studied a meta-reasoning approach for this problem. So here we're looking at our team of UAVs, and some of them can communicate, as shown by these little blue links, and some of them cannot, okay? But the agents need to decide how they're going to collaborate. So this is the meta-reasoning problem that they're faced with. It's a version of the algorithm selection problem. And so perhaps we might have a policy where the agents that can collaborate, these here, might choose one collaboration algorithm, and the other agents might choose some other way of performing the mission. Now, that's fine, but we have this multi-agent system, so even how do we do the meta-reasoning becomes kind of an issue. So we did a survey of research on meta-reasoning in multi-agent systems, and we identified numerous structures that people have proposed and used, and two of them are shown here. The first one here on the right is a decentralized meta-reasoning structure, and you'll notice that the agents are communicating and coordinating at the meta level. That is, they're just collectively deciding how they're going to decide. Over here on the left, we have an independent meta-reasoning structure. Here, you'll notice each agent's meta level is independent of the other agents. They're communicating instead at the object level. Now, in this project, we chose this meta-reasoning structure for our approach because we believed that it would be more robust to the lack of communication. Even if communication was unavailable, each agent would still be able to meta-reason and still be able to choose some collaboration algorithm, which was the whole purpose of our project. Now, at the agent level, we now have, an object level, this big orange box. And here I'm focusing on the task planning. Of course, there's many other things that have to be done at the object level. And we have the meta level up here in this blue box. So at the object level, the agent has to process the sensor data. It has to update its beliefs. It has to identify which tasks need to be performed. It needs to allocate tasks, that is to decide what it's going to do, and then plan those tasks and then execute them. And the whole time it's communicating with the other agents if it's able to. Now, on top of that, we added the meta level, and the key state variable for the meta reasoning policy was the communication quality. The agent is able to estimate how well it's communicating with the other agents. And if that communication quality is high or medium or low, the meta level selects a collaboration algorithm and then tells the object level to use that algorithm to allocate tasks. Now, the particular meta-reasoning policy that we chose to implement was based on extensive experimentation with different collaboration algorithms in different scenarios with different levels of communication. And we used the results of those experiments to derive our meta-reasoning policy. And we then conducted additional simulation experiments to evaluate that meta-reasoning policy. Okay, so here are some of the results of our work. These approaches were done, these models or scenarios were tested with the Rayleigh fading model, where the communication quality depends upon the distance between the transmitter and the receiver. We looked at different types of search problems that are listed here. We looked at different communication scenarios where it changed over time during the mission. We looked at the distance traveled, which is a surrogate for the time to complete the mission, and we looked at the communication quality. Now, in some cases, we see that the meta-reasoning policy dominated the other solutions, and in other cases, we see that there was a trade-off between the meta-reasoning policy and the other policy. But in general, we found that using the meta-reasoning policy reduced the amount of time required to complete the mission, and thus we saw that the meta-reasoning was able to improve the system performance with minimal overhead. Okay, now turn to a different project. This project is part of the Artemis cooperative agreement with the Army Research Lab. We had a couple of students on this project from the University of Maryland, and we had a number of collaborators from the Army Research Lab. And really this project was building on prior work that the ARL collaborators did, and I'm very grateful to them for participating in this project. Here we were looking at meta-reasoning to increase the capabilities of robots, multi-agent systems, and human-machine teams. This project is ongoing, but today I'll just talk about one of those tasks, which was related to thermal management. Okay, so in this figure kind of shows our approach, but before I get to that, the problem we were looking at is the problem that can occur when we have a processor on a robot that's continuously processing, incoming images, right? Using some kind of neural network or object detector or whatever, right? And if that continuous processing increases the utilization of the processor, and that increased utilization can increase the temperature of the processor up to undesirable levels that will stress the processor, degrade performance, and shorten the lifetime or lifespan of that processor. So we really want to engage in some kind of thermal management to avoid those excessive temperatures. Most processors do have a mechanism of dynamic voltage and frequency scaling to help avoid that problem, but we're trying to keep the temperature at a level where it doesn't even have to implement that hardware approach. So here we have our approach. We've got the images coming in. We've got an object detector. In this research, we looked at the efficient det family of object detectors. We've got a processor like a Raspberry Pi. We also looked at an NVIDIA Jetson Nano board. Now, the key state variable here is the temperature of the processor. And the meta-reasoning policy makes a decision or uses a rule to, based on the temperature, determine which algorithm should be run and whether or not a pause should be inserted. So by inserting a pause, we're inserting a little bit of idle time. And so that reduces utilization and helps with the temperature management. But we also wanted to look at, looking at different object detectors as well. So we had some meta-reasoning policies. We had one meta-reasoning policy that had a fixed algorithm and just adjusted the pause. But we had other policies that adjusted both the algorithm and the pause. Okay. So here are some results from Michael Dawson, who just finished up his MS thesis in mechanical engineering. And these are some results from the work that he did on Raspberry Pi. And so let me walk you through this. We'll start down here in the lower right-hand corner. So this meta-reasoning policy was switching algorithms. You'll see that in the beginning of the run, when the temperature was low, it was using the largest object detector. But then over time, it was switching between different object detectors. And as the temperature continued to increase, it was more often using smaller image object detectors. Now, at the same time, the meta-reasoning policy was inserting pauses in order to keep the throughput nearly constant. So it's switching algorithms, but then it's changing the pause length. If it switches to a smaller object detector, it can insert a larger pause and still maintain the same throughput. Over here on the lower right, we can see that the CPU utilization is decreasing. In the beginning, it's quite high, but as the meta-reasoning policy switches to the other algorithms, the CPU utilization goes down. And this led to what we wanted, which was that the temperature remained around this target. Okay, we see some variation around the target temperature, but it avoids this area up here, which would invoke throttling. Okay, so here we see that the meta-reasoning can maintain the desired temperature by switching among the different algorithms and inserting pauses appropriately to keep the utilization reasonable. Okay, so here are some of our publications that have come out on this work. And I'll just make a few comments. So we're currently continuing to work on meta-reasoning for multi-agent systems, for human-machine teams. Well, we do plan to implement meta-reasoning in the ARL ground autonomy stack on an unmanned ground vehicle this summer. But really, all of these tasks are laying the foundation for a more comprehensive meta-reasoning approach that will enable an operationally rational robot that can optimize its reasoning processes given finite computational resources and size, weight, and power constraints. Thank you.